My name is Cihan. I'm VP of Product at Redis Labs. I've been in the database world for quite some time. I've actually worked on a lot of databases. I always do this. I got to find out if you guys have worked on any of the other databases that I've worked on. Started with, I met this guy called Michael Stonebreaker many, many years ago, and he had a product called Illustra. Anybody remember Illustra? All right, there you go. And that was the first database I started on. Informix, anybody work with Informix?
I worked in Informix.
Okay, excellent.
No.
SQL Server?
Of course.
All right, many years at SQL Server. SQL Azure? This is what I get usually. And then Couchbase. A few, all right, okay. And obviously this is the best one. So I don't have to remind you of that, but it is the best one. And I'm a database geek. I've worked on many of these products. And today, we're just going to talk about building large-scale databases on Redis. There's a couple of interesting challenges that I want to talk about. And then I want to throw in a solution that I think is going to work really well. I also have a partner, Frank Ober. I'll let you introduce yourself.
Sure. I'm Frank Ober. I'm a solutions architect at Intel up at the SSD Design Center up in Sacramento. We host people like Redis Labs. We also test open source and work on scale-out storage. We're big in Ceph and things like that in my team. And I'm glad to be here. I'll be talking more about the timings of the hardware, understanding storage class memory against NAND-based SSDs. I think many of you may not know that, so.
And they're right here.
Oh yeah, so I'm going to give away a free SSD. So, stick till the end. You get one of our overclocked SSDs. And if you want to actually see an Octane or buy an Octane server, I'm the guy to actually talk to, because I've touched Octane memory more than anybody in this room for sure.
Very cool. Very cool. So, all right, let me kick into high gear. So it's there's a couple of things I want to walk you through. I'll introduce Redis Labs just a little bit. How many people use Redis Enterprise? Nobody. Maybe one.
There's a couple.
Okay.
There's
a few people. All right. I'll introduce our products, and then we'll talk about this challenge of building large databases with Redis. Obviously, the big challenge here is that we're in RAM, and RAM is expensive. So we'll talk about why and what can actually help resolve that issue, and how we can actually pump in a lot more data into Redis. And then at the end, I want to bring Frank in. We'll talk about performance and some of the changes in the hardware space that are happening that I think are very, very interesting to hear about. Fundamentally, the whole talk is really centered around the fact that we at Redis Labs believe that the evolution of hardware is actually leaning more towards memory becoming the center of compute, and real-time processing becoming a lot more interesting and center of attention in the next decade. So with that, we think that the architecture that we have and everything I'll show you today hopefully makes a great deal of sense when we put it right next to some of the things that Intel is doing and others are doing in this space. All right, so with that, let me introduce the company quickly. We're the company behind the open source technology. I work with Salvatore closely, and many of the contributors who actually contribute directly to the open source are with us. We work on that technology. We're also the provider of Redis Enterprise, which is the technology that we built around Redis that allows us to get scalability, high availability, much better multi-tenancy, et cetera. So there's a lot of IP that we've built, and I'll show you the architecture a little more. We're a fairly young company in database years. We're almost a baby, and we're based out of Mountain View and Tel Aviv. So we have Redis Enterprise as kind of the core technology that sits in the center of things, but we provide the technology as a managed service in the cloud. So if you're on AWS, Azure, or any of the other public cloud vendors, you can actually get this as a service. You don't have to manage anything. You just have to tell us where you'd like your Redis database to be, in which geography, in which public cloud, and we'll actually just provision it for you. And you can also get this capability in your own VPN. So if you want to own your own data, if you want to run this on your own compute and have us manage it through a pipe we create between you and us, to our DevOps team, we can do that as well. So you can completely run this in your own VPN, no problem, and that's called Redis Cloud Private. It's actually previewed a new experience around it today. So Redis Cloud Private is easy to sign up for. You can just go and fill a form, and you'll actually end up with a cluster at the end of it, if you just give us the database size and the throughput that you want. We also provide it as an on-premise solution, so if you want to run this by yourself, you're more than welcome to it. You can take Redis Pack, run it yourself on-premise. Many of the customers do. We actually provide, the technology that I'm going to talk about is going to refer to that flash portion that you see at the bottom. So it does not apply to the Redis Cloud, but everything else will actually eventually have this technology. All right, so with that intro, I'm actually going to go into this problem of how to build a large database with Redis. Now, when I ask people what's great about Redis, everybody says, well, it's fantastic, it's low latency, the data structures, it actually helps me take the beating away from my relational database, and we can use it as a core database in many of the scenarios that I have. These are all great. The problem comes down to it is expensive to put a lot of data into RAM, because just the reality of the cost of RAM is it is $10 to $20, depending on who you buy from and what type of memory you're actually looking at. But it's an expensive per gigabyte figure compared to Rust drives or SSDs that you actually use. So the difference, it turns out, per gigabyte is about 10 to 20x. This prevents a lot of people from putting a lot more data into Redis. This is a quick chart. It shows kind of the quality. The latency goes up a little bit towards the SATA end, obviously. NVMe is much more strong. But the price difference here is about 10 to 20x between both ends of the spectrum. So what we think is the right way to store this larger data is actually to use the emerging hardware and technology, which is getting faster and faster, which is flash memory and the NVMe SSD material. So that we can serve it at the speed that you're used to, which is what you expect out of Redis, but be able to store a lot more of it for cheaper. There's a couple of dynamics to this that I'll explain. So one of the important things that we think we can actually do with this technology is we take a different approach compared to many of the other databases that you've worked with, which spills data to disk. Now, you can certainly do that. If you go buy SQL Server, Mongo, et cetera, you'll actually find that you'll have a portion of your data in RAM and everything on disk. They have to make this durable. They work in a specific way to be able to manage the reads and writes, but they depend on the disk to be a durable material for them so that they can recover under failures. Now, in our case, we actually use it differently. We use the flash memory, the SSD, as a RAM extension. And I'll explain this concept of the difference between the two. It's very important to understand the distinction because it gives us an edge in being able to utilize and exploit the power of this technology. The RAM extension essentially is to give you a better cost-effective storage model. But for all intents and purposes, you can think of this as a contiguous RAM space. So what we actually allow you to do is store a portion of your data that is frequently accessed in RAM and extend the rest of your work, the data size, onto flash so you can store the rest of the data there. And if you need to access it, there's a small latency penalization that happens, which is what we have to do to bring it back into RAM. But other than that, you actually don't realize. And it actually turns out most of our customers also have this characteristics in their workload where they really don't access every key in the system with the same frequency. So it turns out if you have a website, there's only a portion of your users that are logging in all the time. There's a subset of your users that are active at any moment in time. And what we call this kind of hard portion of the data, it's the working set of your total data. So for most people, it turns out that you have to keep this data online, but because it's not accessed very often, it's okay to put it into a lower tier storage other than that. Obviously, nothing is faster than RAM, but it is okay to store more data by extending your RAM. Now, there's also another cloud architecture current that makes this very interesting, and that current is about the ephemeral storage. So either you're containerized or virtualized somewhere. But all of those technologies essentially mean that you have some local storage that you can use, but you can't really trust that to be durable. And the network attached storage that you get with EC2 or other stores essentially is the durable writes have to be a network write. It has to be mounted to the machine, so if your machine comes alive anywhere else within the larger data center, your new machine can actually go access and rehydrate that data back. Now, the ephemeral storage, unfortunately, is wasted in a lot of the databases. If you're using SQL Server or something else, you're going to not be able to use that thing for anything other than tempDB, right? It's temporary data. It gets erased every time the machine restarts. Well, in our case, because we treat the flash area as a RAM extension, we're perfectly fine with you getting rid of the data. If the machine restarts, it's just like RAM, it just resets itself. And we maintain our durability essentially through either the RDB kind of snapshots or AOFs, or we provide replication, which is a much faster way in which you can actually create durability. So typically what we actually also find is that the replicated durability is much, much faster than trying to store data on every replica onto the disk drive in the cloud, especially because of this network write problem. So the ephemeral storage is something we can actually exploit fairly well with this technology. And I'll let Frank talk about the future of technology that's coming from Intel, but we think that some of those things that are going to happen in the next few years as this technology matures is just setting the table for us to exploit this hardware. So cost is fairly easy to kind of peel back. What we're going to look at is, in the next slide, I'll show you how we calculate a 10 terabyte data store and what it would take to build that with RAM only versus RAM plus flash. And the calculation will pretty much, I mean, this kind of gives up the punchline here, but is about a little over 80% in terms of cost savings. So this is about the difference between a $20,000 bill in the cloud versus a $80,000 bill in the cloud. Right? That's the difference. The comparison here, I'll let you guys take pictures, or these will be material that will be available to you. But we've used, on the left side for Redis on RAM, we've actually used the instance type on AWS that has the cheapest gigabyte for RAM. That turns out to be the X1 series that AWS provides. And for us to build a 10 terabyte in RAM capability with replicas, et cetera, it takes a little over $1.5 million a year. Compare that with Redis on Flash, we pick a slightly different instance type, i3. It has a slightly more expensive RAM gigabyte ratio, but it actually has SSDs, a fast set of SSDs built into it, and the cost is drastically lower, as you can see. All right, so hopefully this convinces you that extending your RAM into Flash is a great idea if you want to keep pumping more data into Redis and storing a lot more data for real-time access. Great question. So I'll repeat the question. What is the performance difference between the two? And it is great. If I can hold it for a little bit, what I want to do is take you down to the architecture of this, and we'll talk about what happens in the access path when you actually access it, and that will unpack it. But the way you put it is very true, which is the answer is, as always, is it depends. Depends on the access path. So let me take you through the architecture. We'll start at the top level at the cluster, and I'll zoom into each one of the layers that we we actually run. So at the cluster level, this is Redis Enterprise cluster. It's different than Sentinel and Redis cluster that you have in the open source. The red tier, the slice of that cake that you actually see there is open source Redis. We change it slightly, and I'll talk about how we actually change it for the extension of RAM, specifically in detail, but there are quite a few other differences between the open source, et cetera. But fundamentally, this cluster looks, feels, and smells just like Redis to any application. So if your application is a Redis application today, all you need to do is change your connection string to point at Redis Enterprise, and it will continue to work. Every node is the same. It's a shared nothing architecture. You can just keep adding more nodes. That gives us more computational capacity, and we can just scale further for your workload. If I zoom into the node, I just want to unpack a few of these blue boxes. So what you see at the bottom is Redis shards. We have many of them in each node. And it's up to you as to how many of them you want to get. But if you have, it typically depends on how many cores or what type of workload you actually have. At the blue layer, we have a couple of components that do the trickery for hiding all the details behind the scenes. So proxy is one of those components that really create an interesting capability for us. Proxy is there to manage connection handling, and it ultimately is responsible for scaling connectivity. There's a famous problem of multiplexing. If you have hundreds of app servers and tens of nodes of Redis or hundreds of nodes of Redis, then the multiplexing ends up creating quite a large number of connections if you keep connecting to each shard separately. So each machine can contain many, many shards, et cetera. And proxy actually gives you a way to prevent that multiplexing. So we run one of them per node to be able to manage your connectivity. It also does trickery around pipelining, so that the requests that are coming in from multiple clients can actually be pipelined into the shard that is responsible for handling it. And we take advantage of the pipelining right within the cluster itself. And that gives us an edge to be able to kind of scale a lot of to a large number of connections, but at the same time give you lower latencies. Cluster manager is responsible for the cluster's health. For the most part, it's the governor of the cluster. It decides which node is up, which node is down, and who needs to kind of come onto the stage and leave the stage. So adding nodes, removing nodes, all of those dances that we orchestrate are done by the cluster manager. Secure UI is the way in which you operate the cluster. So this is the REST API or the UI, and everybody goes through that funnel to be able to manage the cluster. So that's there as well. It runs SSL based or HTTPS-based connections for the administrator to come in. Now, I'm going to zoom further to answer your question, into Redis a little bit. So what I'm going to show you first is going to apply to open source Redis for the most part. We're going to simplify things a little bit, but I'll tell you where the differences pop up. So Redis is single-threaded. There's an event loop at the top, and this is what famously makes Redis so efficient and effective. It's a lock-free architecture. Everything lands here, and the essential process is to pick that request up. And then request, I know you guys can't read most of these things, so let me try to see if I can zoom into some of this. On the left side, what you see is a connection handler. So if this is coming from a new connection, we actually establish the connection object. The connections are persisted. Just like any other database, then we have command handlers. Essentially, we need to make sure that what you've sent us is a command that makes sense. It's a verb that we recognize, and it's a set of parameters that we can actually understand. And then we have a set of dispatchers at the bottom. So just like Salvatore talked about this morning, the modules, which is huge, has a dispatcher of its own. So if you're doing, I don't know, some JSON processing in a module that you've created that has a data type, we can actually pick that up, pick that command, and the command handler will actually give it to the module dispatcher, and it will execute. Or the regular commands will actually get executed by Redis itself, but they actually pretty much have the same level of priority. Now, on the right side of this slide, there's a whole bunch of background services. We were just talking about this before we started to talk. So there are a set of longer running operations that we have to run. We have to find out who's expiring within the key space. We have to understand how to evict who to evict, depending on the policies that you've actually set. So all of those things happen in the background as background processes, or writing to storage, taking a snapshot or an AOF kind of write. Those are all things that we actually have as background processes within the architecture. Let me zoom out and show you a little bit more of the, that was the process space, so let's take a look at the storage space a little more. What you see, which is the lighter gray, is the RAM. There are keys, and there are many of the types that are hanging off of it. So keys and values in RAM, not surprisingly. And then the storage in this space essentially is used for the RDB or the AOF file that you want to create for persistence and durability, disk persistence and durability. All right, so that's the Redis. Fundamentally, there are differences between that and the Redis shards that we actually have, not in the way they kind of expose the verbiage to the application, but how they execute some of the operations are quite different in Redis Enterprise. But there's even a bigger difference when you actually start utilizing the flash memory in Redis Enterprise. So one of the fundamental differences between the RAM extension method with Redis Enterprise Flash that we actually use is within the storage space, we not only can store things in RAM, but we will actually push some of them onto Flash. The way we decide what to push onto Flash is based on the least recently used algorithm. So we look at what your working set is accessing constantly, and we'll push things off that are not frequently used out into Flash. Now, from an application standpoint, they are still accessible. It's just that when you try to access it, you'll have to bring that back into RAM and then serve it. So the operations themselves continue to operate within RAM. And if you continue to access the key, if that user suddenly turns up after months of being absent, you can actually hydrate that user back, and that user continues to have a faster experience staying in RAM, right? And you can adjust the ratio between RAM and Flash as well. So, this picture kind of looks like a 50-50 split. It's up to you as to how much RAM and how much Flash you actually want to have. You get to configure this fairly simply, and I'll actually show a quick demo of how you do that. So let's walk through the read and write operation very quickly. Just for those of you in the back, I'm going to zoom into this a little bit. So step one is your application, as I said, is just a Redis application. It connects in. It will send the command. Proxy is going to be the one that's receiving it. It's actually capable of handling multi-key operations as well. So there may be operations that you will send into the proxy that span across the cluster. It will be intelligent enough to go tackle all of those for you, but those requests are going to be then passed down to the specific shards that handle that part of the key space. And if they're being resharded or if they're being rebalanced to other parts of the cluster, proxy is aware of all of those things and will actually coordinate the dance to make sure that you can actually, you're not falling into some black hole or a ditch. Anywhere it actually gets to access those shards, compile the response, and send it back to you. And in the case of Flash, if it turns out that the value that you're trying to operate on is on Flash, we're going to have a fault, a RAM fault, that's going to bring that value out of Flash into RAM before we serve it. So to go back to your question about what's the performance hit, the performance hit is based on how many of those keys, how much of a RAM hit ratio you have, and how much of a fault you're having, which is, how many of those values are you trying to hydrate back into RAM from Flash. And typically what we'll do is, we would like you to be, obviously it depends on your performance expectations out of the system, but the better the RAM hit ratio, the better your throughput and latency. So we actually give you a quick dial to kind of extend RAM and allocate more RAM if your working set is over time growing. All right, so that was the walkthrough of a read and write operation. Let's see a quick demo. I have actually, let me make sure that it's running. I have Docker on this machine with 3 nodes running. I'm going to generate just some, it's a small amount of load. Let's see if it actually gives us a prettier graph to look at. but don't look at the throughput because this is not going to be
Local.
Yeah, this is not going to be high performance, so don't expect a lot out of my old laptop here. So first thing is the nodes. I can actually be here. You're looking at 3 nodes that are running. I have a certain amount of shards in there that are running across these nodes. They report their status, and it looks like everything is healthy. I've got a database here. By the way, the shards actually mean Redis instances that were running. So you saw 3 and 3, which is 6 instances of Redis that are running in the cloud. This is Redis Pack. So the UI that you get in the cloud is very similar but slightly different. This is what the database view looks like. So now I'm in SampleDB. I'm looking at the top level, the throughput and the latency. What you can do is essentially see a full year worth of data, if that's what you have. You can drill into specific shards and look at the specific shards or the specific nodes within the environment. But what's probably more interesting, other than read and write latencies, et cetera, that you can see, is when you create a Redis on Flash database, you can see things like the RAM hit ratio and the amount of RAM usage that you have currently. I don't have the type of workload that actually creates a lot of faults on this machine, just so that the presentation will actually run smoothly. But you can obviously overload. What you would see is a lower percentage of RAM hit ratio if you were trying to access the data on Flash. And that's how we report it back to you. It's a pretty similar concept to what you would normally get from a disk-based database, except in this case it's a RAM extension, and the RAM fault represents essentially an operation to bring it into RAM. I just want to show you quickly how easy it is to change the database. These are database properties, and the RAM to Flash ratio is this slider right here, which I'm going to move just a little bit. So essentially what you're doing here is setting up the percent of Flash and RAM that you want to get. You give us a total amount of RAM capacity that you want to allocate, and then decide what percentage of it should come from the RAM on the machine and what percentage of it should come from the Flash memory on it. So it's as simple as changing this and pressing update, and then we'll actually do the right things to go shuffle things around for you. All right. Any questions so far? Yes, go for it. That's a great question. So how do we expire something when we actually, now one of the big advantages of the Flash extension is that we actually are very selective, and Frank will talk about some of the other technologies that are kind of simulating something similar. But what we have in Redis shards is we're aware of what is valuable for the data access, and we can actually make intelligent decisions about what to push into Flash. Expiration is something that we actually have in the key metadata, and keys stay in RAM. So keys do not get to travel into the Flash memory, and that makes them readily available and accessible. So any operation that you're doing on the key, if you're just retrieving the key, if you don't need the value, there's nothing to fault about, so we can just use RAM to get it.
So I understand correctly, it's a requirement that all your keys have to fit in your RAM.
Correct. So this means that all of your keys have to fit in RAM. Exactly. Yep. There's a couple of differences I want to point out here. I've talked about this in the beginning of the talk, that obviously worked on a number of different systems where we built disk-based databases. And when it comes to writes and the utilization that you have of the I/O path, it is very different as to what you do with that drive if you're extending RAM versus if you're using it as a durable storage. Right? So the RAM extension method, one of the important things that is different about it is the hot value handling. So it turns out your working set is that 10%. Those customers keep coming back and logging in, and your store is trying to kind of validate and authenticate all of those people that are coming to your site. Let's take that example. And that 10% constantly comes in and logs into your site. Those active users are constantly active. What that means is, if you're tracking what they're doing on the website, you're constantly writing to those keys. Now, in a durable system, what has to happen is that those writes have to go to disk eventually. But because we're extending RAM, the hot values that we write to do not have to be sent over as a disk write ever, unless you obviously have AOF or snapshot, but we can actually constantly write to them in memory without having to impact the flash memory at all. So if you're constantly writing to things in RAM, there is practically no I/O path getting exercised for the extended flash side of the house. Another important thing is when you're writing durably, so in Linux we actually use RocksDB, when you're writing durably, there are assurances you have to have in that write. So when using RocksDB, you'll have to enable, if you were MongoDB and you were using the disk as a durable storage, you will have to say, well, I need a write-ahead log write, as well as a key write into this database so that if something happens, I can actually recover my database from the disk storage. Now, in the RAM extension method, we don't need a write-ahead log. We don't need a transaction log. All we need to do is just constantly write to that flash with as little as possible. This is essentially a minimization of the write amplification that you get. So write amplification is essentially defined as a single write causing multiple writes in the I/O path. The reason for that is because there are multiple things that you have to typically write. Maybe you have to move things around to be able to make that write, or you're writing into write-ahead log. So a write amplification write with the flash extension method is much lower compared to a durable database writing using RocksDB. That's another important thing to remember. Yes?
Another factor for write amplification, which is, at least for SSD drives, you have to write a full block, which means if you had an even small facet of the block, usually it will be counted as the full block. Does it happen the same for the flash or not?
Correct. So your question was, well, there are other types of RAD amplifications. Obviously, I think it's safe to say most of the time, if you're writing into a key value store, a single write is never a single write, it's multiple writes. And yes, there are other types of write amplification. We can't prevent every type of write amplification that happens by the nature of the SSD, just because SSDs actually have to do certain things. So no, not every type of write amplification goes away, but the bigger costs come from write-ahead logs, et cetera, because they have to be sequenced so that you can be recoverable if you die in the middle of that write and the engine has to recover. We have no such concerns. We actually can throw away our RAM extension because what we expect is when we come alive, well, it's going to be empty, right? So we can reset the store and we don't have to worry about any of those things. So that's the difference there. And the ephemeral storage, we talked about that, but this ultimately means that if you're on EC2, if you've got ephemeral stores, then you are going to be able to utilize that for the Redis Enterprise Flash capability. So we use the local drives to be able to do that. Obviously, in a durable write, you'll have to use the network attached storage, and that's a network write, and it's a lot more expensive compared to the local write that you have to do. And finally, Frank will talk about the future-proof technology that we have. So before I hand it off to Frank, I just want to share one quick performance point with you. This is a comparison of Octane and P3700, which is an NVMe, an older NVMe technology. Octane is something that we've actually been experimenting quite a bit, but this is what gets us excited about the future of the memory technology that's coming. We think that there's a lot of interesting technology that will come online in the next couple of years. And those are the things that really make this technology much more interesting for us. In this case, we were comparing a 50-50 read and write on a 1K item. And the blue bars that you see, the throughput figures, are a little over 2 million, 1.3 million, and 0.5 million on the blue bars that you see. So these are specific cache hit ratios that we've actually had. But this shows you how fast this technology is growing in speed and in capabilities. So we'll get there. With that, I'm going to hand it off to you to talk about.
Thank you, Cihan.
Thank you.
So yeah, this is the key thing on this slide is 50-50 read-write, right? And that's where we get this 9x inflection, because they're actually doing a lot of writing. So the first thing that you want to learn about Octane is it's very write capable, right? We've built this new media, 3D Crosspoint. You've probably read about it. And every Octane SSD out there, that when you hear Octane, that's the solid state drive marketing term for anything based on 3D Crosspoint. Right, so the thing, we did a lot of testing and we said, hey, you got to crank up the write load. Okay, let's go to 50-50. And that's where we got this number after a few weeks of testing on our Octane drives. What I want to show you is 3 things today: where Intel is headed, some qualities about storage class memory, because many of you have never heard about storage class memory. And what is storage class memory? That is Octane SSDs. That's our offering of storage class memory. And then finally, looking at the use cases we see. So I'm kind of broaden the ecosystem around other applications that you may be looking at and other components, because Redis is very critical, but you want to kind of see Intel's view of how we segment use cases for Octane and 3D Crosspoint. By the way, 3D Crosspoint will also be available on the DIMM, so that's a different technology. I'm not going to talk about it. It's a different class. I'm going to talk about the SSDs being used as a RAM extension, right? So that's we get a lot of confusion from even PhD students at the best universities in the world about what is an Octane SSD. It's a block mode device running over NVMe, NVM Express, right? That's the storage protocol we care the most about at Intel. We don't do anything with SAS, and SATA is going nowhere. Although SATA is still, more than 50% of the market, everything Intel does, all the innovation around faster machines is NVM Express, right? So if you haven't tested an NVM Express drive yet, you probably should try and get your hands on one, because they're a lot better. They actually use 50% less CPU cycles than a SATA device, and I can show you the blog and the testing we did for that. So if you get those CPU cycles back and they're not being used for storage I/O CPU cycles, your application and user space get that to be used for feeding Redis, right? So what we're investing in is a factory to build 3D Crosspoint and these Octane SSDs. They're on the market. We launched them in March, and Redis was a close partner with us on the launch in March. And just this past month, we've launched our first 3D NAND-based SSD. So the follow-on to the P3700 that you saw on the previous slide, we've now launched the P4500 and the P4600. So 3700, there'll never be a 7 again, which is high endurance. You'll buy an Octane SSD, which is several times more endurant than any NAND product because of the way NAND memory is compared to this new type of memory, which is not flash. 3D Crosspoint is not flash. You don't flash that product. So hopefully that makes a little bit of sense. So this is the way we see the world. There's not many DRAM manufacturers anymore. There's 3 of them in the world, and there's 4 3D NAND technologies out there. Besides ourselves and Microns, there's 3 others. So it's a pretty concentrated group of people building the world's flash, and we're actually in a supply shortage right now, and that's why DRAM prices are so high, like the Google guy said in the keynote today, because Google has a problem with DRAM cost. We all do. The whole world has a DRAM cost problem. So this is the way we qualify an SSD. So we'll use FIO. Hopefully you've heard of Flexible I/O Tester, right? Written by some of the best storage people in the world. It's a free utility that you can use to actually test an SSD. You should test your SSDs before you throw your Redis cluster together, so you can make sure you're getting spec, right? I mean, that's what every benchmarker should do. You should work on bare metal with containers so that you can get better performance, because there is a lot of additional latency in KVM, kernel virtual machine, a lot of in the Azure stack. I know the numbers. I'm not going to repeat them up here, but it's pretty high, right? And you're not going to get the best performance that you want from an Octane. You want to be running on bare metal. And if you need to know where you can get a bare metal service of Octane, I'm the guy to talk to. Throughput-wise, where does an Octane SSD actually shine? It shines at the single thread level where you're actually syncing, and it's about 10 times faster than NAND. And so storage class memory, the way IBM defines it, is a device that can go under 10 microseconds. and these devices go under 10 microseconds. In fact, one of these devices with our storage performance development kit can actually do 1 million IOPS at 4K, read and write, right? Because it's symmetrical. That's something that NAND can't do. It can't be symmetrical. It can't read and write both, 500K IOPS here, 500K IOPS here. It doesn't matter, read and write, right? That's why we cranked up the 50/50 test here on the Redis Enterprise. Quality of service. This is where we're 100 times better than NAND. Our 99 number on Octane is 10 microseconds. The 99 number. Go look at what a 99 number is on NAND. That's our 99 number. Our 59's number is under 60 microseconds, right? NAND SSDs go into the milliseconds at these levels that I'm talking about. Why do they go into the milliseconds? Because NAND is extremely difficult to write. You have to write at the page level. NAND pages are getting bigger, not smaller, because we just talked about 3D NAND, right? And we're just going for volume. That's not what 3D XPoint is about. It's about incredible quality of service so that it can go on the DIMM. Because this thing's competing with DRAM. It's got to go on the DIMM, right? Latency, 10 microseconds. I just told you that's the definition of storage class memory. You can bring it down to about 7 microseconds. The PCIe bus cannot go faster than 6 microseconds, folks. Bus trace. Ultra endurance, 30 drive writes per day on this device. So go look up NAND devices. Nobody's doing 30 drive writes per day. So, how do we define use cases for this product? Fast storage, that's what Redis is. They're using storage to extend memory. We call these hybrid memory applications, right? They're taking RAM and extending it onto block storage. That'll also happen on the DIMMs, right? Because the DIMM will be able to come up as volatile memory, because you can use 3D XPoint memory volatilely, or it can be non-volatile. And if you want to know about that, go to pmem.io, and we wrote a whole bunch of libraries over the last 5 years on exactly how to do this when it sits on the DIMM. But the SSD is over NVM Express, right? So you're going to use the 8 or so commands that NVM Express uses, and there's a lot of storage engines out there. There's literally hundreds of key value stores out there. RocksDB is the one these guys are using, which is very, very popular because it's backed by the world's most popular social network. Extend memory. This is very, very interesting. We already are selling Octane SSDs with a virtualization technology that puts these in the virtual memory pool, right? So what happens is you put 4 Octanes in a 2-socket server. They don't show up as block devices. You do ls block in Linux, you don't see anything. What happens is the virtual memory pool just went into the terabytes, right? And so, we partner with an Israeli company, and they basically take this and extend RAM at the operating system level. Right? So that's what they're doing. So it's basically operating system extension of memory. Another thing we did is our developers have been working for 9 months on this. In 4.11 kernel, we have basically made Linux OS paging capable of saturating an Octane drive. It was a lot of work. If you need the set, I have the full documentation set on how to build a server. This is not supported by Red Hat yet. It's not supported by Canonical. None of these guys have it yet. But if you're an innovator that wants to build a box that can maximize OS paging, we have that capability as well. So, that's where we see extend memory. We believe fast storage is better for guys that are in enterprises because there's the intelligence in their product, right? They know how to evict. They can set patterns, and they can actually work in the user space, right? User space is always more intelligent than the OS space. So that's, if some people are trying to figure it out, right, the Redis product and products like that, there's a lot of products coming in this space, are going to be more intelligent. So I'll take questions now, and then if there's no questions, we'll give away the SSD.
When you say you're in partnership with the company for extending the memory, does it mean you have to buy equipment?
No, you buy a bundle. You buy the Octane SSD with the Intel memory drive technology option, and we bundle.
You can plug it to any other server.
You can plug it into any server. It's good for 2.6.32 kernels and forward. It runs on generic Linux kernel. But it basically, now you're putting a proprietary extension into your kernel, right? It's about 5 mega code. It's not that much. Does that answer your question? Yeah, you buy from us. They're not a marketing company. They're purely a technology company. They're called ScaleMP.
So how do you compare the OS level extension of extended memory versus application level extension of Redis Flash?
Well, one is you just bring your apps, right? So if you just want a couple terabytes of virtual memory, or you want to use OS paging, you just bring your app. So we see a lot of the HPC guys and the Scholastic guys, they want to do this stuff. Some of the cloud developers that want to have large memory pools because they know their virtualization isn't using full DRAM bandwidth. Most of the world's applications need memory capacity. They don't need the 35 gigabytes per second that exists on the DIMM bus, right? If you have a high bandwidth DRAM application, you don't buy memory drive technology. If you need tens of gigabytes, that's how fast the DIMM bus is, right? We're 2 gigabytes per second on every Octane SSD. So I mean, Pete, there's a huge gap between what PCI can do and what the DIMM bus can do, and that's why this stuff's so exciting to put on the DIMMs.
No,
Right?
the point is,
The difference. Sorry, I think I wanted to just tag on one more thing to the question that you asked. The difference that I see is we're very selective about what we push to flash and what we don't. And that kind of intelligence is only possible, I'd argue, at the level where you understand the internals of your application. And that's why the efficiency of what we do, keeping keys in RAM and writing in certain ways that actually only satisfy the requirements we have, these are all the things that you can be smart about. Paging at the operating system level, I know, is a way in which you can get any application to work, but it's not going to be intelligent about what to page out and what to page in, just like any operating system isn't.
so you think the performance in terms of IOPS or latency will be better if you go with your solution versus this solution?
Absolutely. We've tested open source Redis on this paging stuff. Absolutely. Absolutely. The Redis product is way better with this thing.
Okay.
I don't have these numbers, but in-house I know it's
Okay, thank you.
absolutely.
I thought nobody was going to ask a question just to get the SSD, but
People like SSDs. All right, so I mean, we're good time. Do you want to? The first hand that I see, I'm going to pick. I'm going to ask a really simple question. What are 2 features about Octane SSDs that make them different from NAND? The guy back there. Very good. It's all about the latency, guy. That's what people pay for, right? And we're about 10x better on a single thread. So this SSD is yours. And I'll
nice.
You go, sir.
Thank you very much. I appreciate all of you staying. If you want to, this technology is available at Redis Enterprise right now if you want to download it or try it in the cloud. There's a whole bunch of ways to get engaged with us. So I'll leave this up. Come find us outside if you got questions. I know the next presenter want to settle in. Thank you.